Hi everyone, welcome to Data Science on Greenplum classification using the MADlib machine learning library. My name is Woo Jung. I'm a part of the data science team at VMware Tanzu. And in today's hands-on tutorial, we're going to be walking you through some code and some concepts around the following topics. We're going to begin with some preliminaries and some information and code on how to connect to Greenplum. We'll follow that with some data exploration and feature engineering using SQL and some Python extensions. We'll then go into exploratory data analysis, or EDA, and we'll make use of some summary statistics, capabilities on Greenplum, along with making use of visualization tools in Python to help us with EDA. The fourth section of today's tutorial is going to be focused on model training. And for the purposes of that section, we'll actually make use of the Logistic Regression module in MADlib. And last but not least, we'll also spend a little bit of time to walk you through some code on model evaluation and prediction. With that, I'm going to jump over to Jupyter Notebooks. And we're going to start by going through some preliminaries and showing you how to connect to Greenplum from Jupyter Notebook. Along with this recording, we'll also share some links for a couple of options around how to download a VM or a Docker image that you can use to try out some of the code that I'll be executing in the tutorial. The other thing that I should mention here is that to allow us to write SQL nicely in Jupyter Notebooks, we're going to be making use of the SQL Magic extension. And I've shared the GitHub repository here for the extension. And if you haven't yet installed SQL Magic in your Jupyter Notebook environment, please go ahead and do so. I highly recommend it. And then let's see, the other thing that I should mention here, of course, is a big thanks to Hongdon Lee from the VMware Tanzu data science team for building up this training material and allowing me to actually make use of it to record today's session. Thanks again, Hongdon. Okay, so let's begin. We're going to actually start by loading up the SQL extension that I just mentioned. And so I'm going to do that. It looks like it's already loaded in my Jupyter Notebook environment, so that's good. The next thing we're going to do is actually we're going to connect to a Greenplum environment from our Jupyter Notebook. This is one example of a VM of Greenplum that I have running on my laptop for demoing purposes. But please do note that your IP address, database name, and port and password are obviously going to be different from what I have here in my local environment. But here again, I'm going to be making use of the SQL Magic with the %% prefix to let Jupyter Notebooks know that I'm going to be that I'm going to be executing SQL. Okay, I'm going to run that, and it looks like I'm now connected to the database. To keep things tidy, we're going to store all the tables and artifacts in this module in a schema named classification _ MADlib. I've already created the schema, so I'm going to skip running through that section of the code. But I encourage you to either create a schema named this classification MADlib, or a name of your choice so that you can keep all of your code and your tables tidy. Another thing that we'll do here is, just so that we don't have to keep typing the schema name when we're referencing objects and tables throughout the tutorial, we'll set the search path to the schema for convenience. And that's the next line of code that I'll run. Looks like we're all good. Okay, so we have connected to Greenplum database from Jupyter Notebook, and the next step here is now to load some data. I guess many of you might be familiar with this Abalone data set, and because it's so widespread and well known by the data science community, we decided to make use of that here for today's tutorial. The next few steps are actually going to go through how to download and load the Abalone data into Greenplum database. There's a whole wide range of different ways of doing this. And here we're just going to make use of Greenplum's external tables functionality to load that data set into our environment. After we've created an external table to load it into the environment, we'll also materialize the external table into a table for convenience. Okay, so that's the next section here. We're going to create a table containing information on Abalone. And these are the columns that are contained in this file, the CSV file. And the URL for the source data is written down here under the location argument. So I'm going to go ahead and execute that SQL. It looks like we have created that external table successfully. So let's take a look at a number of sample records from the table, and also do a count on how big this table is. So it should be fairly small, about 4,177 rows. And then let's also take a look at 10 random rows from the table. So here you go. So we have information on the abalone sex. We have information on the length of the abalone, diameter, height, a whole bunch of other features that are collected about abalone. As I mentioned earlier, we're also going to materialize the table locally for convenience. And if you notice up here, there actually isn't a ID column that's included in the original data. So we're going to do that. We're going to add in a column for ID in the process using the row number over as ID SQL command that you see here. And let's run that. Looks like we're all good. We'll do another count just to make sure that we got all the records. So yes, 4,177, which matches what we had up here. And then let's also take a look at 10 records from our materialized abalone table. Looks like we're all good. You'll see that in addition to the original set of variables that were included in the raw data, we also now have an ID column that represents that allows us to keep track of what records are where in the data set. And actually, just to make sure that we did this correctly, let's do an order by ID. Yep, it looks like we're all good. Okay. So far we haven't done anything really interesting. We've just connected to the database and we've loaded some data into it. So the next part is where we're going to do some exploration on this data and then start to do some feature engineering. The first part of this is creating our response variable, right? And let's suppose that our goal here using this data is to predict whether or not a given abalone is mature. And we're going to kind of define maturity based on the number of rings in the abalone shell as a proxy. Right? If you'll remember from above, we have a column named rings in this table, right, which contains this information. And to approximate the abalone's age, let's set age to the number of rings plus 1.5. Right? Let's also assume that a mature abalone is one that's at least 10 years of age. Again, using our rings, number of rings plus 1.5 approximation that we just mentioned. We'll use this column to create a binary column to represent maturity. And in SQL terms, we're going to be using a case when statement to get this done. Okay. And ultimately, when we get to model training later on in today's tutorial, we're going to be making use of logistic regression to actually predict whether or not a given abalone is mature. In other words, whether or not a given abalone is at least 10 years of age. The other thing that we'll do in the next part of the data preparation step is that, for simplicity, we'll only keep sex, diameter, and shucked weight in the process table. Okay. So again, we'll just take another look at 10 records from the table. Looks like we're all good. And then we're going to do a couple of things here. We're going to first include the column that we're calling mature, excuse me. And this is when we're going to make use of that case when statement. So when the number of rings for a given record plus 1.5 is greater than 10, then assign a value of 1 to this column. Otherwise, assign a value of 0 for this column. Okay. So we're going to create that table. This table is now called Abalone version 2, v2. Let's see, let's take another look at 10 records from that table. And now we'll see that we have a column named mature. And yes, we see that this is equal to 1 when rings plus 1.5 is greater or equal to 10. So let's take a look at some examples here. So mature is equal to 0 for this particular abalone, and that's correct because there are 7 rings, and 7 plus 1.5 would be 8.5, which is less than 10. On another case, we have one where an abalone has 10 rings, and 10 plus 1.5 is greater than 10. So in this case, mature should take on the value of 1. So it looks like we're good and that we have created the target variable or the response variable that we want to predict in this analysis. All right, so the next part here now is to compute and review some summary statistics. The MADlib machine learning library contains a convenient function to compute summary statistics from a given table. And we're going to be making use of that function in the next block of code that we execute. As you'll see over here, we're going to supply the name of the source table. And in this case, it's going to be that Abalone version 2 table that we just created. Right? The next argument is going to be where we supply a name for the new table that will be created by MADlib that contains the results of the computed summary statistics. And again, for simplicity, let's just call that Abalone v2 summary. We also supply and specify columns from the source table, right? This is the source table, well, excuse me, that we want to compute summary statistics on. And in our case, let's suppose that we want to compute them on the diameter column and the shucked weight column. And so we have diameter and shucked weight as values for that next argument. And finally, you can also do group by. So the MADlib function allows the end user to specify a grouping column that allows you to do aggregations on the dimension that you supplied. And in our case, let's say we want to compute summary statistics for all records where sex is equal to M, for all records where it's equal to F, and for all records where it's equal to I. And I believe I stands for infant in this data set. Okay, so we've walked you through the different types of arguments that are available in madlib.summary. So let's run that, and it looks like we have successfully computed the summary statistics. And let's now take a look at the set of statistics that are computed by this function. Right? We're going to make use of the information schema table, which contains metadata about the database that we're connecting to in Greenplum. And you can see that there's a whole wide range of different statistics that are returned by the MADlib summary function. There's quite a lot of information there, so rather than look through everything, let's actually just take a look at a subset of these statistics. Excuse me, namely row count, missing values, the mean, standard deviation, and then the interquartile range that we get back from the summary statistics results. Okay, let's do that. So I'm going to run this code that selects a subset of these statistics that are computed by the MADlib summary statistics function. And we see that not only are the subset of metrics that we've specified returned, but that as we had originally instructed MADlib to do, the function returns aggregated statistics across all of, grouped by the variable name sex, and then also aggregated across all values. That's actually represented by the records with none under the group by value column in this summary table. So let's take a look at an example for, row count. So here we see that well, maybe I should say the average or the mean, sorry. So the value of diameter, the average value of diameter for female abalone is 0.45. For male abalone, it's about 0.439. And across all abalone, it's about 0.40 or 0.41. And that average is brought down because in this infant group, we see that, as expected, the mean diameter is markedly less than what you'd see in adult females and adult males. Okay? And similar types of statistics are returned not only for diameter, but because we also supplied it as a column of interest in this command up here, we also have summary statistics for shucked weight that are returned by this function. Okay, we've taken a look at some descriptive statistics about the abalone data. The next section of the tutorial is going to focus on exploratory data analysis, or EDA. We're going to be making use of Python for visualizing this data. And to do this, let's begin by saving data from Greenplum as Python objects, and then using libraries in Python to generate our plots. I guess one thing to keep in mind and to notice is that we're going to be making use of this double arrow operator in SQL magic for object assignment. And so what's happening here is we're creating an object in Python called df abalone. And it's going to contain what you get back from the select statement over here. Okay. Let's run that. Looks like we're good. The nice thing about SQL Magic is that you're now also able to use the result sets data frame method to work with these objects as pandas data frames. And so I'm going to show you what that looks like here. And as you can see, we have all records from the original source table, Abalone v2, now represented as a pandas data frame. Okay, so next we're going to use this data frame to generate a scatterplot matrix. And the reason why we do this is to visually assess potential relationships between each of the variables that we have in our data set. Okay, so we're going to import some libraries to help us do this. And then we're going to run some code to generate the scatterplot matrix. And here we go. We have now represented here a scatterplot matrix of 3 variables that we've included or specified to Python, right? I guess the first thing that you should notice here is that given that metrics like the diameter and the shucked weight of an abalone are most likely related to each other, right? We see that there are some correlations between these variables, as you can see from the visualizations here, right? And it looks like the abalone in the infant group, which is represented, by the green data, might have been from an earlier version of the script here, from the green data. This may exhibit different patterns in the abalone than the male and female groups, right? So this is nice. It gives us a kind of a visual way to explore the data and help us assess and look for patterns that may help us when we're training models to predict whether or not a given abalone is mature. But as an alternative to these visualizations, we can also compute the Pearson correlation statistics between each variable pair, so diameter and shucked weight, for example, using a module in MADlib. And MADlib has a module, a function called madlib.correlation. And we're going to be using that now to compute the Pearson correlation statistics for our variables of interest, namely diameter, shucked weight, and mature. We're going to assign the output of the correlations computed in Greenplum as a Python object, just so that we can look at them nicely. And supporting what we saw in the scatter plots, it looks like there are some strong correlations between diameter and shucked weight, right? Earlier, we also saw that there might be different patterns exhibited by the data depending on the sex of the abalone. And actually, to do this in a little bit more of a detailed way, we'll also take a look at a box plot and examine whether we can uncover some patterns there. Okay. So we'll start by plotting the diameter variable in a box plot. And it looks like the mature abalone here, which is summarized by the orange boxes, generally have a higher value of diameter, right? Compared to the non-mature abalone, or those that are less than 10 years of age. The non-mature abalone are represented up here in the plot by the blue boxes. And we've also grouped by the box plots based on the sex explanatory variable. And we see that this difference in diameter between a mature abalone and an abalone that is younger is consistent across all three groups, even at the infant stage of the abalone's growth, which is interesting, right? In addition to the diameter feature, let's also take a look at the shucked weight variable. So we're going to generate an equivalent box plot for the shucked weight variable. And we see here as well that the shucked weight for mature abalone are generally higher than that of abalone less than 10 years of age. Again, here, this is, I think, what we'd expect and is in line with what we'd try to explain and observe from a biological perspective, which is great. Okay, so we've done some visualizations to explore the data, and I think the next part of the tutorial is going to be on model training, namely using classification to predict whether or not a given abalone is mature. Okay. One of the variables that we want to include as a predictor in our model is the one called sex, and this is a categorical variable, right? Not a numerical variable. To be able to use categorical variables in logistic regression models, we need to do something that's called one-hot encoding. And we'll show in the next block of code here how you can make use of MADlib's encode categorical variables function to get this done. Okay, so let's begin by taking another look at the data. It's the same one that we've been looking at and that we've been exploring together till now. The next block of code is going to actually do that one-hot encoding of the sex column, right? So we're going to run that code here. The first argument here is the name of the source table, right? Abalone v2. The second argument is a proposed name for the output table. Let's call this one abalone one hot. And you also supply the, oh, there's a typo there. It's a categorical columns to encode. And we did that. And let's take a look at now the results. What's returned by this MADlib function in the table called abalone one hot. All right, and comparing to what we had before, which is here in the upper part of the screen, you'll see that there's kind of a pivoting that's done, right? So for ID number 1, the value for the categorical variable is M, and you'll see that here it's done a little bit of pivoting, and so sex underscore F is equal to 0 for ID 1. Sex underscore I is equal to 0, and sex underscore M is equal to 1. because in the original categorical variable, M was the value that this particular record took on. Right? I guess for another example, record number 3, which has a value of F in this column, you'll see that now it only has a value of 1 in sex underbar F, and then has values of 0 in the other 2 dummy variables. Okay. So in essence, we've seen that the function MADlib encode categorical variables has correctly mapped the categorical columns into 3 binary columns. The next thing we're going to do is actually split up our data set into training and test. The training set will be used to build our candidate models, and the test set will be used to evaluate fit and performance. To do this, we're going to be making use of the MADlib test split function, and yeah, we'll get right to it. I guess one thing to note is that for reproducibility, we're just going to be making use of the set seed function in Greenplum. Okay. So here we go. There's a function in MADlib called MADlib train test split, and the first argument is the name of your source table. And we're going to be making use of our latest version of the table, which is called Abalone 1 hot, okay, the one that we looked at just before. We also supply a proposed named for the output table. And here we're going to call this one, let's say, Abalone 1 hot split. This function allows you to specify the proportion of records that you want included in the training set, and conversely, the proportion of records that you want included in the test set. Let's do an 80% to 20% split here, and so we'll supply 0.8 and 0.2. Okay. We're not going to be doing stratified sampling in this case, and we're not going to be doing sampling with replacement. We want separate output tables for train and test, so we're going to say true here to that argument. And then you can also do a selection on the columns to output into the training table and the test table that the MADlib train test split function is going to generate. Okay. So now that we've specified those parameters in this function, I'm going to go ahead and run it. Looks like it has run successfully. Let's count at let's do a quick count on number of records that are in the training set. So about 3,342. Likewise, let's do a count on the number of records in the test set, about 835. And just to check whether that split is roughly okay. It looks like we're good. So if you divide 835 divided by the sum of 835 and 3342, we get back about 20% very roughly. Let's now take a look at a couple of records from the training data table, right? So let's do that over here, and we see that Abalone 1 hot split train contains the same set of columns from the original table, but just a subset of the records. Okay, so now that we've done the training and test split, we're now ready to train a model which predicts whether or not a given abalone is mature. Again, we're kind of using our heuristic definition of whether or not an abalone is mature. And in this case, we're going to assume that mature is equal to at least 10 years in age. Okay. We decide to use MADlib's Logistic Regression module to do this. And I'm going to walk you through here again some of the parameters and arguments that you would supply into this function. First of all, the name of the function is MADlib log record train. And the first argument is the name of the source table. So our source table containing the training data is called Abalone 1 hot split train. So we're going to specify that here in this for this parameter. We also propose a name for the output table that contains the regression summary statistics. So we're going to call that MADlib logit fitted. In logistic regression, you have a target or a response variable that you want to predict with the data. And for logistic regression, it's specifically a binary variable that you want to be able to predict. And so in our case, whether or not a given record in the data set contains information on a mature abalone. So whether or not an abalone is greater than 10 years of age, that's going to be the variable that we want to predict by using this logistic regression model. Okay. So now that we've specified the response variable or the target variable, we're also going to be making use of the explanatory variables in the data set to generate those predictions, right? So here we specify the set of variables, the set of columns in the one-hot split train table that we want to make use of as explanatory variables. We express that as an array. One here is for the intercept term of the regression, and then the specific variables that we want to use to predict abalone maturity are diameter, shucked weight, whether or not the abalone is female, and whether or not the abalone is an infant. We're not going to be doing group by modeling here, so we're going to keep that column, keep that expression null. And then logistic regression, in this module, we're able to specify the maximum number of iterations that we want to ask MADlib to go through, and let's just set it to 500 for the time being. All right, so we're gonna run this model now, and it looks like it has completed. The 500 iterations have, that it has completed, so I don't think it has gone through all 500 iterations. Didn't need to. Let's take a look at the results of the regression model, okay? And here we're going to be taking a look at the summary statistics and the odds ratios, right, from the regression. And we'll get back a set of values for each of the explanatory variables that we have supplied in our original model training statement, right? So the intercept term, diameter, when sex is equal to female, when sex is equal to infant, and the shucked weight of the abalone. And so it looks like we're all good. After we have trained this model, it makes a lot of sense to evaluate it and assess whether or not the accuracy is of a quality, that we're comfortable with. And so we evaluate the fit of the model in this following section. Let's begin by computing the predicted values for the test data set, right? So up to now, we've trained our models using the training data, but remember we did that 80% to 20% split, right? And so now using the 20% of data that we've blocked out, that we've treated as, quote unquote, out of sample, we're gonna evaluate how the model is doing on that test data set. And to help us here, we're gonna make use of MADlib's prediction function for logistic regression. We're going to create a table that stores these results on the test data. And the first thing to note here is that MADlib actually supplies two versions of the predict function. One is predict prob, which generates the probability that the given record based on the model should be assigned to the class mature. The other one is actually a binary prediction. It's basically just ones or zeros, and it's based on that predicted probability that we just talked about. So this MADlib log rigor predict function is going to return a 1 if the predicted probability is greater than or equal to 0.5. And it's going to return a 0 if the predicted probability is less than 50%, less than 0.5. Go ahead and run that block of SQL there. And let's take a look at a few results from this table. So, just 10 random records from the test data set. And you'll see here now we get this predicted probability that's returned. The last column here is the actual value of mature that we see in the test set. And then this mature pred column is basically equal to 1 if the predicted probability is greater than or equal to 0.5, and as we just talked about and explained, equal to 0, like this case over here, when the predicted probability is less than 0.5. At least for these 10 records, it looks like it's generally doing okay. It did a misfire here where it predicted 0 even though the actual class was mature, but then for most of the other records here, what's predicted and the value of the mature column and the actual test data are aligned, which is great and which is what we want to see. We can also compute what's known as the confusion matrix to sum up and check how the model is doing overall by using MADlib's function for the confusion matrix. The function is called MADlib.confusionMatrix, and the first argument that you want to supply to it is the name of the source table. So it's the one that we just generated up here, right? MADlib logit predicted class. We also then propose a name for the output table, and let's call the output table MADlib logit conf.mat. You also specify the predicted value and then also the actual value for both what the logistic regression is aiming to predict, and so the predicted class of the model along with the actual values. Okay, so let's run that. Looks like we're good, and we're gonna also now take a look at the results here. And so this is a 2x2, and so you generally want to see values that are lining up with each other, right? In this diagonal. So you want to see more numbers, more cases, more counts in this sort of lower left to upper right diagonal, right? Let's take a look at an example here. So 509. So this means that when an abalone is actually mature, the model is correctly predicting that the probability is greater than 50% in 509 cases, right? And in the remaining 37 cases where the abalone and the actual data was marked to be not mature, the model misfires. And so there's a bit of a model error here. And then conversely, for all the abalone in the test set that are less than 10 years of age, represented by a 0 in the actual data column, we see that 199 records we've correctly predicted, and 90 records the model has misfired in. So yeah, a couple of errors here, but then I think overall this is a good fitting model based on what we see in the confusion matrix. Okay. In addition to this confusion matrix, you can also make use of the numbers contained in it to compute standard methods of assessing model quality like precision and recall. And we're going to be doing that actually back in Python now. So we're going to assign a local variable in Python called df_madlib, which contains the results of this MADlib logit predicted class table, right? The next thing we're going to do is we're going to make use of some code in Python to actually compute some common statistics for assessing model quality. Okay, so as you can see here, I won't go through all the numbers, but we have a precision of about 0.85 and a recall of 0.932, and the overall accuracy score is 0.848. So generally, we see that we have a model that fits fairly well. In addition to these kind of point statistics or point metrics that summarize the overall model fit, you can also compute the area under the ROC curve, and then also visually plot it. And so let's start with simply computing the area under the curve, the ROC curve, using a MADlib function that helps us do this. So there is a MADlib function called area under ROC. And the way this works is you supply as its first argument the name of the source table. So it's that same table again, MADlib logit predicted class. You supply also a proposed name for the output table. Let's call this MADlib logit AUC, area under the curve. You also specify where in this MADlib logit predicted class table, the source table, the predicted probability column, what the name of the predicted probability column is. And then also specify the name of the column in the source table that contains the actual value of the target that we're trying to predict, in this case, mature. Okay, so let's run that. And it looks like, yes, the area under the curve is about a 0.89, which again, I think generally that's a fairly good fit for this type of data. We're going to be using some capabilities in Python now to generate the ROC curve visually. And this is the last part of today's tutorial. Let's go ahead and execute the function here. And we see that the ROC curve has been generated using the metrics that we've supplied to Python, right? And just a quick check on the AUC, the area under the curve. Python has it as 0.891, and that's in line with what we've computed in MADlib over here. Okay. So actually that takes us through the tutorial for today. We used a TOEI data set, the Abalone data set, to show you how you can actually build machine learning models, specifically logistic regression models, to predict a binary outcome of interest. In this case, it was whether or not the given Abalone was greater than, is 10 years of age or older. Excuse me. We've actually gone through quite a few different capabilities in MADlib, in SQL, in Greenplum, and in Python to help support this type of pipeline. We hope that this was helpful, and please do reach out to me with any questions. I'll leave my email in the accompanying material with this video recording, and I'll be happy to get back to you and chat. Thanks again. Take care.